Today we're going to take another look at converting rational numbers to decimals, and this time instead of using equivalent fractions we're going to be using long division. Now what you're going to need for this lesson is your calculator for part of this, and again your math journal and the worksheet that you are given in class. Alright, let's start off with some question and answer notes in your journal. So can we find the decimal form of 1/6 by writing it as an equivalent fraction with only factors of 2 and or 5 in the denominator? So think about that, or write out 1/6 by factors and see if there are only 2's and 5's in it. Well, if you did that, you would notice that 1/6 is 1 over 2 times 3. So there are no factors of 3 in the numerator, which is up here, which means we can't cancel out this 3 in the denominator, so the 3 has to remain in the denominator. This means that we can't write the denominator as a product of only 2's and 5's, therefore the denominator can't be a power of 10. The equivalent fraction method that we used in the last lesson will not help us write 1/6 as a decimal in this case. So is there another way to convert fractions to decimals? Well, you kind of got that answer on the title screen. And since a fraction is interpreted as its numerator divided by its denominator, since 1/6 is a fraction, we can divide the numerator 1 by the denominator of 6. So use the division button on your calculator to divide 1 by 6. So use your calculator to actually do this, and you would type in 1 divided by 6 and get an answer for that. So what do you notice about the quotient? Remember, quotient being the answer to a division problem. You probably notice that it doesn't terminate, and almost all of the decimal places have the same number in them. Alright, so now let's flip over to your worksheet and let's complete example 1. So using the division button on your calculator, explore various quotients of integers 1 through 11. Record your fraction representation and their corresponding decimal representation in the space below. So you're doing 1 through 11. So 1 divided by 2 would be 0.5. 1 divided by 3 is 0.3 repeating, so on and so forth. So if you started with 1 and as your numerator and your denominator is 2 through 11, then these would be the type of answers you would get. So what two types of decimals do you see? Comparing these up here, what types of decimals do you see happening? Well, some of the decimals stop and some of them fill up the calculator screen, or they keep on going. So let's just revisit the definition of terminating and non-terminating. You don't necessarily have to write this down unless you have forgotten what they are. But a decimal is called terminating if its repeating digit is 0. So if we keep getting 0 as our answer, as we keep dividing using long division, then we never write the zeros at the end, so we just stop with the first non-zero digit. The decimal form of a rational number, for example, 1 over 3 is 0.3 repeating, and we usually use the bar notation over the repeating digit. So a non-terminating decimal is a repeating decimal that is not 0. Alright, so let's go back to your journal. Did you find any quotients of integers that do not have decimal representations? Well, your answer would be no, unless you're dividing by 0. And since we can't do that, all quotients have a decimal representation, but some do not terminate or end in this case. They keep on repeating. All right, so let's go to example 2 on your worksheet. In the chart below, you're going to organize the fractions that you just did in example 1 and their corresponding decimal representation according to their types of decimals. So, what types of decimals do we have? Well, we have terminating and non-terminating, so that should be the headings to your T-chart. Then go ahead and split up those decimal representations into the ones that are terminating and the ones that are non-terminating. And you should have something that looks like this. These 5 fractions are terminating, and these 5 fractions are not terminating. Okay? So what do these fractions have in common? We're down here answering this question under terminating. Well, each denominator is a product of only the factors 2 and or 5. So here's a 2, here's 2 2's, here's a 5, this is a 2 times 2 times 2, and this is a 2 times 5. So all of these have a denominator with a factor of 2 or 5, and or 5. Over here, the denominators contain at least one factor other than 2 or 5. So we have a 3, we have 2 times 3 here, we have a 7, we have 3 times 3, and we have an 11. All right, so example 3, converting rational numbers to decimals using long division. Using the long division algorithm to find the decimal value of minus 3/4. Now again, you can use your calculator to double check your math, but you have to show your work. So I expect to see the long division method on your paper. So the fraction is a negative value, so its decimal representation will be as well. So negative 3/4 is negative 0.75 or 75 hundredths. So again, we know that the opposite of 3/4 is equal to negative 3/4, which is equal to 3 over negative 4. So we use our rules for dividing integers. Dividing 3 by 4 gives us 75 hundredths, but we know the value must be negative, so the answer is negative 75 hundredths. All right, go ahead and complete exercise 1 on your worksheet, and when you are done with that, then continue the video to check your answers. All right, so again, using the long division, negative 7/8 should be negative 875 thousandths. 3/16 would be 1,875 ten-thousandths. All right, example 4 on your worksheet. Using long division to find the decimal representation of 1/3. So if we set this up, 1 divided by 3, notice what happens. And they've worked this out to a couple different place values just to show the pattern that is happening. And they've circled what is repeating. Is not just the 1 but the 10. Each time you bring down a 0, you keep ending up with a remainder of 1, or 1 left over. So the remainder repeats, yielding the same dividend remainder in each step. This repeating remainder causes the numbers in the quotient to repeat as well. Because of this pattern, the decimal will go on forever, so we cannot write the exact quotient. Remember, this is always an estimation because we're trying to turn a number that is not a factor of 10 into a form of a number that relies on 10 as its place value and as its answer. And 3 will never go into 10 equally. All right, so think about this. You don't have to write it down unless you feel it's important for you to remember for next or for later. What part of your calculations cause the decimal to repeat? Well, when a remainder repeats, the calculations that follow must also repeat in a cyclical pattern. So cyclical meaning that it goes around and around. It just keeps doing the same thing. So causing the digits in the quotient to also repeat in a cyclical pattern. So you keep doing the same thing. If you always end up with 1 as your remainder, you're always bringing down a 0, and so you're continuing that cycle in that process. All right, so exercise 2. You're going to complete this on your worksheet by yourself. When you're done with exercise 2, go ahead and continue the video. All right, so for A and B, and they went ahead and really identified the repeating remainders just to get an idea. Express your answers using bars over the shortest sequence of repeating digits. So here's where we again revisit bar notation. If we know that the repeating decimal or place is going to be 4 repeating, you don't have to go on past maybe the 3rd time to know that it's not going to change. That means the 4 is the only digit that will repeat, so we're going to put the bar over the 4. Now again, do not forget, this is a negative, so don't forget the negative in your answer. Same thing with 1/11. Sometimes you have to go a little ways to figure out what is repeating. In this case, it's not just one digit, but it's 090909. So the remainders repeat in a alternating pattern of 1 and 10. So you end up with 10, then you end up with 1, then you end up with 10, and you end up with 1, and so that's how the 0, it becomes 0 and 9 and 0 and 9, so on and so forth. So the way we read, again, a negative fraction means a negative decimal, so it's 0.9 repeating with the bar notation over the 0 and the 9. All right, here is C and D. Go ahead and compare your answers. Notice how long it takes 1/7 to start repeating. So it goes on quite a while. All right, let's do example 5 in your math journal. So the long division algorithm will either terminate with a 0 remainder or a remainder that will repeat. Why? So in the first case, the long division algorithm terminates with a remainder of 0. So why does that happen? Well, the decimal also terminates. So when you have a division algorithm terminate with a remainder of 0, that means the decimal answer or quotient will also terminate. In the second case, the long division algorithm does not terminate with a remainder of 0. So what is happening there? Well, let's take a look at 1/7 from your previous exercise. There is no 0 remainder. It never ends in 0. So the algorithm continues. The remainders can't not be greater than or equal to a divisor of 7, which means there's only 6 possible non-zero remainders, 1, 2, 3, 4, 5, and 6. So that means that the remainder must repeat within 6 steps. And for anything divided by 7, it usually takes that long to start repeating. So if you go back and compare that, notice that they don't go in this order, but you'll have a remainder of 1, and then I think it skips to 4, and then 2, and then 6 and 3. So it never is anything more than 7. It's never 7, but you'll notice the pattern of these rotate cyclically. All right, so let's go back to your worksheet and look at example 5. How did we determine whether a decimal representation of a quotient of 2 integers with the divisor not equal to 0 will terminate or repeat? Well, in the division algorithm, if the remainder is 0, then the algorithm will terminate. If it is not 0, then it is limited to the whole numbers, 1, 2, 3, and it's always one number less than the divisor. So that's what the d minus 1 means. So when we were talking about 7, our repeating numbers are limited to 1 through 6. Okay? If it's 11, then our repeating digits would be limited to 1 through 10. Well, and 10 being a 2-digit number, but 1 through 9. All right, this means that the value of the remainder must repeat within d minus 1 steps. So again, with 7, it has to repeat 7 minus 1, or 6 steps. Given a divisor of 9, the non-zero remainders are limited to the whole numbers 1 through 8. So the remainder must repeat within 8 steps. Well, it obviously repeats sooner than that. When the remainder repeats, the calculations that follow will also repeat in a cyclical pattern, causing a repeating decimal. All right, so example 6. Using rational number conversions in problem solving. So Eric and 4 of his friends are taking a trip across the New York State Thruway. They decide to split the cost of the tolls equally. If the total cost of the tolls is $8, how much will each person have to pay? So if we are setting up this problem, then it would be $8 and divided by Eric and 4 of his friends. So please don't divide this by 4. Eric and 4 of his friends is how many people? Well, it'd be 5. So when you set this problem up, it would be 8 divided by 5. So there are 5 people taking the trip. His friends will each be responsible for $1.60 of the tolls. Now, notice the answer is 1.6, but in the context of the problem, we want to write this in money. So this would be $1.60. So we're going to add the 0 to it. All right, just before leaving on a trip, 2 of Eric's friends have a family emergency and can't go. What is each person's share of the $8 tolls now? So instead of 5 people, it is 3 people. So now there's 3 people taking the trip, resulting in a repeating decimal. So notice what happens if we have 2.66 repeating. Then if I take 2.66 repeating and multiply it by 3, are we going to get $8? No, that's not enough. So we have to round up. So in this case, it would be $2.67. So you will end up with $8 exactly. No, you would actually end up with $8.01, but at least, again, in the context of the problem, 2 people are going to have to pay $2.67, and 1 person would pay $2.66. All right. So in closing, again, in your journal, let's summarize what we've talked about by maybe asking and answering some questions. So what should you do if the remainders of a quotient of integers do not seem to repeat? And what is the form for writing a repeating decimal? How do we write a repeating decimal? Well, you want to double check your work for computational errors, but if all is well, keep going. If you're doing the math correctly, the remainders eventually have to terminate or they have to repeat. And for the second question, using a bar to cover the shortest sequence of repeating digits, which we call bar notation. All right, we'll see you in class.